If you're preparing for a calculus class and you want to make sure your pre-calculus is good, you need to make sure that you understand inverses of functions. You also want to understand analyzing a function if it's even, if it's odd, or neither. This is Math from the Void. We're looking at the Calc prep assignment. This is part 7, and we're starting to get a little bit abstract because we're talking about the inverse of a function, and we're also going to explore the inverse with this phrase here, which is 1-to-1. So in this part 7 cluster of problems, we're really going to just focus on analyzing functions. And in this first example, we're going to find the inverse of a function. So how do we find the inverse of a function? Well, first it could be helpful to note that the inverse of a logarithmic function is going to give us some kind of exponential function. Maybe I should put it as this. A logarithmic function and exponential function are inverses of each other. So if we're finding the inverse of an exponential function, then that means we're going to at some point have, if we're finding the inverse of this logarithmic function, then we're going to at some point have an exponential function. Okay, so let's see what exactly that's going to look like. In order to find the inverse of a function, what we want to do in practice, you might be taught this in class, and I think it's a decent way to describe how to find the inverse, is you start off by replacing f of x with some variable like y, and then we want to swap these variables because the inverse switches the input and the output. Okay, that's what an inverse does. In fact, I think that's a really important note to have. So make sure you have your notebook and get ready to write down some important info. Inverse functions swap the input and output. That's what inverse functions do. They swap the input and output. So in this case, instead of plugging in an x and getting a y, we're going to plug in a y and get an x. Well, if we want to swap them out, now we need to solve for the y variable all over again. And it could be more accurate to say that this is f inverse. But it's going to be kind of like a y. It's going to be the y value or the output value of our new function, which is the inverse function. So then we just follow some basic algebra to solve for this. What do we have to do here? We have a couple of steps. Subtract 4 on both sides first. Okay, what we're trying to do here is we're trying to get the logarithm expression by itself. I'm going to put a y in here instead of f inverse, but we'll just keep in mind that the y that we're solving for is the same thing as f inverse. What's next? Well, we have to divide both sides by -2. And we're going to continue this up here. X minus 4 with a negative in front divided by 2 is equal to the log base 3 of y minus 1. Okay, now that the logarithm is by itself, there's nothing else except for the logarithm and what's inside of the logarithm. We can turn this into an exponential format. And we can do that by noticing that the base here is a 3. So this expression, this equation, is equivalent to the following. 3 to the power of negative x minus 4 over 2 equals y minus 1. So even though that looks messy, this is all the exponent on 3. We're going to add 1 to both sides, and we'll finish off by saying y, which is f inverse, is equal to 1 plus 3 to the power of negative quantity x minus 4 over 2. And that's good enough. It's just an algebraic exercise. So as long as you know how to move the pieces around, that's what we're really testing here. What inspires us to do this in the first place is the concept of inverse, which has us swap the input and the output, the x and the y switch, and then we need to do some algebra to solve for the y all over again. That's really all we're doing. Okay, let's move on to the next. Determine whether the function is even, odd, or neither. This is a really useful skill, especially once you get to calculus. If you know how to use this property well, your life will be easier. Your life won't be impossible in math if you don't know this well, but you can save yourself a lot of time and a lot of hassle by just knowing it completely. So really understand what even and odd helps us with. Let's take a little time to do that. An even function, what does that even mean? You might not remember what it means. An even function means that if we plug in a negative value, we should get the exact same as if we plugged in the positive value. For example, if we were to plug in -7, that should give us the same output as if we plugged in a +7. That's what it means to be even. And what this looks like on a graph is that the left side is symmetric to the right side. That's because like a negative x value out here, let's say this is like -4, it should have the same y value as +4. Let's say that's right here. And that would be true for all of the x values. They would have this symmetry which kind of connects them. Maybe those points go up there. And so there can be like this very interesting symmetry for an even function. Algebraically, it looks like this down here. You plug in a negative, and you get the same thing as if you were to plug in a positive x. This is the classification for even functions. So we want to check to see if it's even. Let's go ahead and do that. How do we check to see if it's even? Well, we have f of x. This is given. That's the equation. That's this, f of x. But what we want to check now is negative x. Rather, I should say f of negative x. So let's plug in negative x to the equation and see what that's going to give us. If I plug in negative x, then that means everywhere I see x, I'm going to replace it with negative x. There we go. Excuse me. And what do you notice happens? Well, if we do negative x, of course, that gives us the positive. But on the bottom, when we square something, it just stays positive or becomes positive if it were negative. So now this becomes x squared plus 5. And you'll notice this is not the same thing as that. It's very similar. How is it different? Can you notice how it's different? Well, because the original function has a negative on it, and now that we've plugged in negative x, there's no such negative. Kind of canceled it out. On the bottom, it did stay the same, x squared plus 5 and x squared plus 5. But since the top is not the same, then these two are not equivalent. In fact, not only are they not equivalent, they're opposites of each other. So, how can we write that? We can write that like this. F of negative x equals negative f of x. So they're not quite the same. They're the same value, but one of them's negative, one of them's positive. Okay? And guess what? So for example, let me show you an example. Like if I plug in -7, that should give me the opposite value, or the negative, of what I would get as the output if I plugged in 7. So it turns out this is the definition for an odd function. Notice the similarity. The even function says that if you plug in a negative, you get the same as if you plug in a positive number, whereas the odd function says if you plug in the negative, you get the opposite of what you would get when you plug in a positive. And what does that look like on a graph? Well, what that looks like on a graph is it does have a kind of symmetry, but it does not have symmetry across the y-axis. Instead, if I were to plug in -4 and get something up here, let's say that's 3, then when I plug in a +4, I'll end up not across here, but rather flipped downwards as well. So I'll have something here at -3. And the symmetry that arises is it's this nice symmetry across the origin. So you might get a function that looks something like this. See how there's symmetry, but it's across the origin. It's not straight across the y-axis. It's like every single point has a sort of sister point or a matching point. Okay? So this is the definition of an odd function. Now, if it were not the same as the original when I plug in -x, and it were also not just the opposite like it was, this ended up being the opposite of f of x. If neither of those two things happen, then the function would be neither even nor odd. Okay, so this function turns out to be odd. Even, we checked it, and that's not true. When you get to calculus and even higher levels of math, it becomes really useful to be able to determine if a function is even or odd. In many different fields of mathematics, that's not limited to one type of field of mathematics. There are several situations where it could benefit you to understand something is even or odd, and it will really simplify your work, like incredibly so. It's particularly useful when you're doing things off to infinity, and you sort of don't need to calculate things off to infinity if you simply understand the properties of the function. But I'm digressing. Let's go on to this next function, which again wants us to find an inverse, but it uses a different phrasing. It asks if the function is 1-to-1. So let's just break down what 1-to-1 means. First, we'll say a function is 1-to-1 if its inverse is a function. That's an easy way to write it. Perhaps a more technical way to write it is a function is 1-to-1 if every output has exactly one input associated with it. So an even function is not 1-to-1, because an even function, if I have a certain output, there might be two inputs that have that output, particularly x and -x. So another way to write this, by the way, I guess I can do it like this so that it's not in the way of my text. Another way to say this is that graphically, the function passes the horizontal line test. I mean, there are several ways to say it, but you can also say every y value only has one x value that goes with it. As you can see, whatever y value this is, it has two x values that go with it. So that's how you can use the horizontal line test. Say if it crosses through horizontal line twice at any point, we know that it will not be 1-to-1. Okay, so we want it to pass the horizontal line test. We do not want it to cross more than once. What kind of functions do that sort of thing? A good example is x cubed. X cubed never has a repeated output, right? Once it hits like this value, it never hits it again. Once it hits this value, it never hits it again. It only crosses through every single output once. So let's take a look at this. If this is 1-to-1, well, I just mentioned that if it's even, it's definitely not 1-to-1. So first let's check if it's even, because then we can answer the question right off the bat, but we'll still do a little more math with it. Let's plug in negative x, and if you do that, you get negative x squared plus 1. That's just going to give us 1 over x squared plus 1. That's the exact same thing as f of x. So if f of negative x gives me f of x, this is an even function, and even functions are explicitly not 1-to-1. That's just one of the many examples that proves my point when I say knowing whether or not a function is even or odd can help you with some stuff. Instead of having to calculate the inverse and figure that out with algebra and then check to see if the inverse is even a valid function, instead of having to do that, I can use the fact that this is simply even, and it was pretty easy to do that. Anyone who thinks that's tough is wrong. It was really easy to check that it's an even function, and since I know what even means graphically, I can say with confidence that it's not 1-to-1. Now let's find the inverse, and I'll confirm that algebraically. So if we start off with y equals 1 over x squared plus 1, and then we swap the variables, so now we have x equals 1 over, technically it's f inverse squared plus 1. But like I said earlier, we can just call it y for now so that we don't have to write that every time. That's really the only reason why we do that. It's not technically correct to just call it y all of a sudden, but we need to solve for the y all over again. And the y is stuck in the denominator right now. We don't want it stuck in the denominator. So what are we going to do? Well, what we're going to do, there's several ways you can do this, but what we're going to do is we're going to do the old flipperoo. We're going to take this equation, which is a fraction equals another fraction, and we're just going to flip the whole damn thing. We're just going to flip it. 1 over x equals y squared plus 1 over 1, which is just y squared plus 1. You get it? I just flipped the whole equation. Flipped it. And now I can solve for y. And at this point, we should have a suspicion that this isn't going to be a function. So suspect that the inverse will not be a function. Why do I suspect that? Because I have a y squared here. And if I'm trying to solve for the y, I'm going to have to take a square root. And whenever I solve with the square root, I get a plus or a minus. Okay, so let's finish this off. Subtract 1 on both sides. So now we have y squared. I'm going to put it on the left side if that's okay. Everyone always flips out when I move the equation and flip it around. They're like, whoa, buddy, what are you doing? It's an equation, guys. The left is equal to the right. So if I want to flip them around, it's totally fine. It's still equal. Y squared equals 1 over x minus 1. And then lastly, I have to take a square root to solve this. So it's going to be a plus or minus square root of 1 over x minus 1. And that kind of reveals as well why it's not a function, because we have a plus and a minus of a square root. Okay, so what would that look like? Interesting. The original function looks something like a bell curve, I think. Similar to a bell curve. So it's not one-to-one because we see a bunch of these horizontal lines that would cross through more than once at two different spots. Except for at the very top, where it's, top of the hill. But everywhere else, it crosses at 2 points. So this function is not one-to-one because its inverse is not a function. All right, that'll do it. That's going to cover our investigation, our abstract exploration from the void, discussing inverses of functions and some properties of functions. Stick around, stay with it. The Calc prep assignment is almost halfway done. Yeah, we've got a long way to go, but don't trip. We're traveling. See you next time.